Imagine stepping into an elevator on Earth's surface, pressing a button and riding smoothly into space. No explosive rockets, no astronaut training required, just a gentle ascent through the clouds and into orbit. This isn't science fiction anymore. It's a serious engineering concept that could revolutionize how we access space. A space elevator is exactly what it sounds like. A cable stretching from Earth's surface to a point 22,000 miles above the equator in geostationary orbit. Mechanical climbers would travel up and down this cable, carrying cargo and passengers to space at a fraction of current costs. Instead of burning thousands of tons of rocket fuel, you'd simply ride upward like taking an elevator to the 100th floor. The concept first appeared in 1895 when Russian scientist Konstantin Tsiolkovsky gazed at the Eiffel Tower and imagined a tower reaching into space. He envisioned a structure anchored to Earth with a counterweight in orbit, held taut by centrifugal force as our planet rotates. Modern space elevator designs follow this same basic principle but replace the tower with a cable. Here's how it works. Earth rotates once every 24 hours. At geostationary orbit, satellites circle at exactly the same speed, appearing to hover over one spot. A cable anchored at the equator and extending past this point would remain stationary relative to the ground below. The portion above geostationary orbit acts as a counterweight, pulling outward as Earth spins, keeping the entire cable under tension. The real challenge isn't the physics, but the materials. The cable must support its own weight, plus the weight of climbers traveling along it. It needs to withstand incredible tensile forces while remaining light enough to be practical. For decades, no known material could handle these stresses. Steel would snap under its own weight. Even advanced materials like Kevlar fall short by a factor of 5. Then came carbon nanotubes. These microscopic cylinders of carbon atoms possess extraordinary properties. They're stronger than steel by weight, incredibly light, and theoretically capable of handling the forces involved. A carbon nanotube cable just 3 feet wide could support a space elevator. That's narrower than most doorways, yet strong enough to reach orbit. But there's a catch. We can only manufacture carbon nanotubes a few centimeters long in laboratory conditions. Creating a continuous cable stretching 22,000 miles remains far beyond our current capabilities. Scientists estimate we'd need nanotubes at least 1 meter long to weave into a usable cable. We're making progress, but slowly. The potential benefits are staggering. Current rocket launches cost between $2,000 and $20,000 per pound to reach orbit. A space elevator could reduce this to around $200 per pound. That's a 100-fold decrease. Suddenly, massive space stations, lunar bases, and Mars missions become economically feasible. We could launch satellites weekly instead of monthly. The journey itself would take about a week. Climbers powered by laser beams from the ground would ascend at roughly 120 miles per hour. Passengers would gradually experience decreasing gravity, reaching weightlessness at geostationary orbit. Going beyond that point, they'd feel centrifugal force pushing them outward, away from Earth. Several organizations are actively researching space elevator technology. Japan's Obayashi Corporation announced plans to build one by 2050, though many experts consider this timeline optimistic. The International Space Elevator Consortium coordinates research efforts worldwide. They've identified over 40 specific technical challenges that need solutions. One major concern is space debris. Thousands of defunct satellites and fragments orbit Earth. A collision could sever the cable catastrophically. Proposed solutions include making the cable movable to dodge debris or building it from multiple smaller ribbons that could survive minor impacts. Weather presents another challenge. The anchor point must avoid hurricanes and severe storms. Equatorial locations in stable weather zones are preferred. Some designs propose ocean-based platforms that could move if necessary. Interestingly, once the first space elevator exists, building additional ones becomes much easier. Materials could be manufactured in orbit, where weightlessness simplifies production. The first elevator would lift components for the second, creating a bootstrapping effect. Some scientists propose building our first space elevator on the Moon. Lower gravity and no atmosphere make it far more achievable with current technology. A lunar space elevator could use existing materials like Xylon, a synthetic polymer. This could serve as a proving ground for Earth-based systems. The space elevator represents humanity's boldest architectural dream. It transforms space access from explosive chemical reactions to simple mechanical engineering. While significant obstacles remain, each year brings new materials breakthroughs and engineering solutions. What once seemed impossible now appears merely extremely difficult. Could the space elevator finally make us a truly spacefaring civilization? And if we build one, what incredible structures might we dream up next?